this. Sorry. Yeah, so now we have Michal Eckstein talking about new foundation experiments with quantum process tomography.
Okay, well, thank you very much. Well, first of all, let me thank the organizers for organizing an event in this beautiful place. So I think we are all looking towards the aperitivo already, so I'll try to be brief. Okay, so we are all after new physics, and there are essentially three routes that you can look for new physics. The first and by far the most common one in particle physics is to look beyond standard model, but still within the quantum field theoretic paradigm. Okay, if you're a bit more courageous, you can still assume quantum mechanics, but then go to general relativity or some other gravity theory if you wish. And then you have all sorts of quantum gravity theories and also the semi-classical approaches. But there is a third route, which is not explored at all in particle physics so far, namely that, well, you want to go beyond quantum mechanics, but still assuming relativity. I mean, you need to assume something to start with. What can be out there? Well, Paweł Horodecki on Thursday will tell you more about that, so I'll just flash it very quickly. So you can have so-called superquantum correlations, which even follow from the Bell inequality violation. You can have a maximal violation of Bell inequality, because the usual quantum value is 2 square root of 2. But you can have a theory in which you have a 4, still with no signaling, so assuming space-like separation, freedom of choice, everything that you want. Okay, another option is the so-called generalized probability theories, which, well, follow from the relaxation of some quantum mechanical axioms. Well, yet another route is to look for deviations from linearity of quantum mechanics. You can do it also at the level of quantum theory if you want. And then there are the so-called objective wave function collapse models, so new theories trying to explain what happens really in a quantum measurement. Okay, and these typically they involve some nonlinearity and also some stochastic element, etc. So there is really a bunch of nice theories that can be considered beyond quantum mechanics. Now, well, what motivated Paweł and me to undertake this study is the following sketchy diagram of our main theories. So people are mostly concerned now with this border between classical and quantum mechanics. So that's the domain of Bell inequality violation, but that's also the domain of the objective collapse models. So people try to understand what happens, how does the classical world emerge from the quantum. Okay, but then we thought, well, but this diagram is much larger, so there are other domains that can be explored. First thing is about the collapse. So the thing is that, well, if you think of a decay process, okay, and well, you all know that in a weak decay process, the phrase is that for instance, the W boson is its own polarimeter, right? So it somehow measures itself projectively, okay? But if you believe in quantum mechanics, that cannot be true, okay? The only projective measurement happens at your final detector and at the moment that you get your final result, okay? So the conclusion from quantum mechanics is that there are no decays, nothing happens, your Higgs boson does not decay, and there is no Higgs boson in the first place because, I mean, it's all a huge unitary process, and only at the final moment when you read out your numbers from the detectors, only then you can say that, well, there was a collapse, okay? So, but then you can ask the question, is that the case? Or maybe there is some objective collapse in this process, okay? So that's a valid question that you can ask and you can try to test. Okay. Second thing, quite interesting, is to explore this border between quantum mechanics and quantum field theory. Okay, so, well, we know that quantum field theory is based on quantum mechanics at the first place, But there are some recent results from that show it's related to the so-called Tyrelson problem, that show that actually there might be a kind of a Bell inequality, so a gap between quantum field theory and quantum mechanics. Okay, so in principle, quantum field theory can allow for correlations that you cannot obtain with the usual quantum mechanics. Okay, whether it's just a formal result or whether it's physical, this is debatable. But again, that's a question that you can ask. Okay, well, and then at the end of the day, you can wonder whether it's quantum mechanics is the end of the story, or maybe there is some deeper theory below it that we just don't see because we don't even know what questions to ask. Okay, so the strategy is how to look for possible deviations from quantum mechanics. So that's an operational question. That's something that we want to do. Okay, so what we do, we approach it from the information theoretic point of view. So the general strategy is the so-called black box approach. So the physical systems are treated merely as information processing devices that are probed by some free agents. Okay, and then your conclusions are drawn from the output-input correlations. So in other words, you will deal with conditional probabilities of your outputs conditioned upon your inputs. Okay, and that's the setting of a proper Bell test. So you have two agents, say Alice and Bob. They have two inputs and they have some black boxes. And they assume nothing about these boxes. They know nothing about these boxes. They know they might be correlated, but they completely ignore the physical details of these devices. Okay? And then they meet and they probe it with their inputs and they register the outputs, and then they look at the correlation functions. Okay? And then from these correlations, they can write down, for instance, the Bell inequality, and then they can see whether it was, what's the Bell value, right? If it's above 2, then you know it's not a local hidden variable theory. Okay, if it's above 2 square root of 2, you know it could not have been quantum mechanics. Okay, and there's a key assumption that we discussed quite a lot during after the first talk of this session, namely the assumption of the freedom of choice. So, or you can call it measurement independence if you don't want to have this philosophical flavor here. So the thing is that you cannot allow for any precorrelations between your inputs, between the inputs themselves, okay, and the box, okay? Because if you do, well, you cannot even, as Juan pointed, you cannot even write down the formula for local hidden variables, okay? Because it implicitly assumes that there is no correlation, it's independent, okay? The thing is that if you violate it, it does not necessarily mean that you have a superdeterministic theory. Okay? You can violate it slightly, so you still have some free will, but not a perfect one. And then you can show that, well, the Bell inequality is violated, but there is a local hidden variable theory that explains it, because you don't have this freedom of choice. Again, this is something that Pavel will cover in his Thursday talk, and I think we discussed. Yes?
How many boxes? You have 2 boxes?
Well, in general, you can have as many as you wish, but here in Bell inequality, you have 2 boxes. Okay?
Which are the same?
Not necessarily. I mean, they are just black boxes, so it's. I mean, they can even have different colors if you wish, but okay. The thing is that there are some physical systems that, well, you suspect they are correlated in some way, but you know nothing about the details of these devices, okay? Okay, but I will make it even more simple. I will just have 1 box. Okay, because, well, we are the quantum guys, so we believe in quantum mechanics. We said, well, quantum mechanics works so perfectly well that, I mean, why should we test it even more? But okay. But the thing is that, so we assume that now our boxes are quantum information processing devices, and they can be probed locally with quantum information. So in other words, what we say that we have some box, okay, which can be, I don't know, which can be this table, but usually you think of your accelerator and you have some region of the collision that you treat it as your box, okay? So there is some ingoing information and some outgoing information, and we assume that everywhere outside of the box, quantum mechanics is valid. So you can process these quantum states in a usual way as you do, but inside the box, we know nothing at all. It can be classical, it can be quantum, it can be post-quantum. You don't assume it, okay? Well, you can have some classical parameters here as well, like the scattering kinematics. And then, well, it is all a part of the black box strategy, because at the end of the day, we're not writing down our quantum states in the lab notes, right? But we're dealing with classical information, so you need to prepare your input state, and then you need to reconstruct your output state, and this you do with the quantum tomography, okay? Now, okay, once you say, okay, this is my box, my Q data box, and I want to probe it with some quantum information, then you make we call it a Q data test. So you just probe the box with the input state that you have prepared, okay? And for every input state, you make the full quantum tomography. So at the end of the day, you have this data set. So for every input, you have reconstructed your output, and if you have changed your classical parameters, you need to reconstruct the output again. Okay, and there is an asymmetry, a very important asymmetry between the input and the output here, because, well, we assume that the input is pure, in particular that it is not correlated in any way, not even classically, with the box, whatever the box is. And that's the freedom of choice assumption, okay? Because if you violate it, then, well, then it's all wrong. Well, then you can see if you can allow for a tiny correlation or so, but you need some freedom to prepare this state, okay? On the other hand, the output state, well, you don't control it in any way, and it can be entangled with whatever else came out of the box or whatever else is out there. So you just register part of your information, so you will get a mixed state in general, because it's entangled with something else, okay? But the good thing is that, well, it means that you don't need necessarily to gather all of the information that comes out of your box. You just can focus on one thing, and then, well, you are going to get a mixed state, which is fine. Okay, so let me give you a short example. Probably many of you have seen it already, but it's always repetitio mater studiorum est. So suppose you just have two available inputs, and then you toss a coin, and then you choose one of them with equal probabilities, okay? And then you ask your colleague, your friend, to guess which of the states you have input, okay? Well, you can quantify the success rate of his guessing, and then, well, if he just guesses at random, he will get it half of the time right. But if your friend knows quantum mechanics, he can slightly improve on that by making nice measurements on these states and trying to distinguish these states. Okay, so if these states are orthogonal, then he can always distinguish them perfectly. So he will always get right, because, well, then if they are orthogonal, this is 0, so the success probability is 1. But if your states are not orthogonal, then he can never get it perfectly. There's always some bias, and this is precisely quantified by just by the scalar product between the states, so the overlap of these states. Okay? And in quantum mechanics, this distinguishability of states, it can never ever increase. It can decrease by the coherence or some other processes, but it can never increase. Okay, so what you do, you try to, well, then you have your data box, Q data box, and then you test it with these two inputs. You reconstruct the output states. And if it turns out that your output states have a better distinguishability than your input states, well, then you know for sure that it's not a quantum mechanical device. Okay, and this can happen even if your input states are pure and your output states are mixed. Well, this is the formula for pure states, but that's just the trace distance, so you can write it for mixed states as well. So if you have a better distinguishability at the output, well, it means that there was something non-quantum going on and beyond quantum. It's not, cannot have been classical as well. Okay, and for instance, all models involving nonlinear modifications of quantum mechanics, they involve the violation of this Hellstrom bound. Okay, so that's one way to test linearity. Okay, so slightly more general setting is the so-called quantum process tomography. So in quantum mechanics, any map from your input states to your output states must be a completely positive trace-preserving map. Complete positivity means that it's, if you tensor your map with the identity on any system, for any n, it must remain positive, okay? So the intuition is that if you, well, you have some map which is positive, but then if you tensor it with whatever else systems, it must remain positive, okay? That's complete positivity. Well, trace preservingness means that, well, it transfers states to states, so this thing needs to be normalized. There is a way to generalize it, so all CPTP maps are called quantum channels. There is something more general called quantum operation, which is still a physical operation, but it's not trace preserving. But then it's just a matter of normalization, so you can always rephrase it as a CPTP map. And because quantum mechanics is linear, and if you assume that your Hilbert spaces are finite dimensional, then your map is just a table of numbers. Okay, and it's completely characterized by a finite number of real parameters that you can recover from your experiment. Okay, well, and very easy way to check if something is CPTP or not is to use the quantum, is the channel state duality. So that's a quantum state which is related to your CPTP map, and it's a two-way street. So it's CPTP if and only if this guy is a quantum state. Okay, so in the language of our boxes, what do you need to do? Well, you need to make a Q data test with a m square input state. So for every input state, you reconstruct your output state. And from these output states, you can reconstruct the map. And then you can see whether it's CPTP or not. And so that's an example from some experimental paper that was superconducting qubits, I think. So you have some input states, that's the tomography of the input state, that's the tomography of the output state. Here you have a different state and a different output state. Okay, so you need to choose your input states from the so-called tomographically complete basis, and then you can reconstruct the entire map. Okay, and the nice thing here is that, well, quantum mechanics is basis independent. So if you choose one basis, one tomographically complete basis, if you choose another one, you should get the same map, the same channel, because it's basis independent. But why not checking? I mean, you can rotate the basis and see if you get the same map or not. If not, well, it means that maybe it's nonlinear, maybe it's basis dependent, but it's not quantum mechanics. Okay, so that's the idea how to use this quantum process tomography to look for deviations from quantum mechanics. Okay, so can we implement that in particle physics? Okay, so that's something that we are now discussing intensively also with Alan, with Pavel and Kazuki. So what it would take? Well, first you would need to prepare quantum programmed particles carrying your input state. So for instance, electron spin or photons polarization. Then you probe a Q-data box, which means that you just collide them. And then you would need to measure projectively all of the outgoing projectiles, and from that you reconstruct the output state, okay? Now, well, in high energies, you cannot possibly prepare individual particles. It's not like with atoms or superconductors or photons, because you have always bunches of particles. But what you can do, you can use polarized beams. So if the polarization degree is high enough, well, it's not entirely a pure state, but okay, it might be good enough, okay? Well, colliding them is easy. This, we know how to do it. And then, at the other end, the trick is that in this scenario, you don't need to measure them projectively. You can let the nature do it for you. And then you just reconstruct the output states, as Alan explained, from Weeks decays. And for the tops, you can do the same for general weak decays, okay? W's, T's, taus, stuff, or Z's. Yeah. That's before my last slide, so I'm that's okay. Okay, so that would be the idea to implement it. Now, so what you need polarized beams. Or a beam and a polarized target. That would also work. Okay, so, well, we want to start with the low-dimensional systems because if you have even if you have just 2 qubits at the input and 2 qubits at the outputs, so this is 4-dimensional, this is 4-dimensional, it means that your Choi matrix, so the matrix describing your channel, is 16 by 16. Okay, if you have Q trees at the ends, that's 16 times 81. Okay, so already these are quite big numbers. Okay, well then the best would be to use E plus E minus colliders because these are clean machines. So one of these processes was analyzed by Clelia Altomonte and Alan Barr in a paper, which I don't know, is it already is it published yet or not?
It's been accepted for publication and might therefore soon be on the archive.
Okay, okay, so, okay, so this is good news. So yeah, so that would be the simplest example. So you use polarized beams of E plus and E minus, and by manipulating the polarizations and reconstructing the output states of the T and T bar, you can reconstruct the whole channel, and then you can see if it's CP or not, and you can look for deviations from linearity, etc. Well, but there is another option. You can use an electron-proton machine, as long as you can polarize the protons as well. And then you can assume that, well, there is some other processes like photon gluon and some other stuff that are being produced. But one of the final products is, for instance, TT bar or some W's. So if you can reconstruct the spin matrix of these guys and you can control the spins of these guys, well, it's still a valid map, okay? So such an operation, well, it's not going to be unitary, obviously, because you have some other stuff that you don't measure, and well, this can be entangled, anything, but it must be complete positive, okay, if quantum mechanics is valid. Okay, so this, well, okay, this is a cleaner experiment for sure, but you can still think of some scenarios for EP machines, as long as you can polarize both things. And these can be beams, or you can have a fixed protonic target as well. Okay, so that's something that we try to explore and write down with Alan, Pavel, and also Kazuki here. Okay, so let me just, okay, yeah, I think I'm doing good in time. We have 3 minutes before aperitivo, so let me just give you the take-home messages. So the first thing that was already said, but let me emphasize it again. To make a proper Bell test, you need at least some freedom of choice, okay? So you need some randomness that is not determined by your system, or you believe it's determined by your system, okay, quantum decays, but you need something from the outside, okay? So just the entanglement detection or quantum state tomography is not a Bell test. It's just a reconstruction of the quantum state, and then you can see whether it's separable or entangled. But you assume quantum mechanics from the very beginning. If you say that, well, okay, the decays are random, so the choices are random, well, that's okay, but the decays are a quantum mechanical process, and you assume they are random because you believe in quantum mechanics, so that's a circular argument. If you want to make a proper Bell test, you need something from the outside of the system, okay? So, well, if you would like to make a proper Bell test, you would need to directly measure projectively the spins of the outgoing particles with the tunable settings. Well, this doesn't seem to be very realistic, but maybe there is some way that you can think of using, I don't know, Stern-Gerlach, for instance, to look at the spins of the outgoing leptons. But okay, but if you can make it, if you can make a proper Bell test, then not only you're testing quantum mechanics against local hidden variables, but you also at the same time testing it against post-quantum scenarios. Because if you get a Bell value which is higher than 2 square root of 2, and then you know that, well, you have closed the loophole, so I mean, you have some randomness that comes from the outside, measurement settings, then, well, okay, it's a signature that it's not quantum mechanics. So then that would be the proper experiment. So not a demonstration of quantum mechanics, just an experiment. Okay, and well, quantum process tomography is a way to, well, it offers new opportunities because, well, you can switch, well, you can shift your problem of preparation at the input, at the beams, at the level of the beams, and then you don't need to bother about the measurements at the end. So you can use it to seek deviations from quantum mechanics, like unitarity, CP, linearity, etc. But at the same time, you can use it to understand quantum dynamics, okay, in high energy physics. So you're not just reconstructing the states and learn something from that, but you understand the quantum dynamics of your states. So, well, I would bet that this can also be useful to look for some new particles and new forces, etc., etc. Okay, and to do that, to implement that, you need to have polarized beams and/or targets. Okay, well, thank you for your attention.
Thank you, Michael, for the nice talk. Actually, maybe I start with a question. Sure. So that this non-unitarity, it cannot for the system to evolve as an open system, it cannot mimic this deviation from quantum mechanics. In particular, in this indirect process that you have E and P, that you have some non-unitarity evolution there. Yeah. This doesn't change the Hellstrom test, or? Well,
I mean, if there's just something non-unitary, the easiest explanation is that, well, there was something else that you don't measure, and your projectile is entangled with that. So that's your environment that you don't control, and, well, it's not unitary, but it's still, but it must be a quantum map, a quantum channel. So it must be CP. So you can, if it's not CP, then that's a different story.
So being non-unitary and still being CP, you don't need to change the Hellstrom test or something.
You don't need to change what?
The test that you were saying, the Hellstrom?
The Hellstrom test.
Yeah.
No. You cannot violate the Hellstrom inequality if you just have non-unitary maps. Because, I mean, this just means that your states are, well, if it's non-unitary, it means that your states are getting more mixed.
Yeah.
But as I said, there is no way to increase distinguishability by that. You can only decrease it.
Because the CP is still this
yes,
CP.
Yes,
right.
yes.
Okay. Thanks.
Just a quick one. On this point about somehow the decays being quantum and random, but that somehow leading to a bit of a circular argument.
Right.
Is this not, I'm not sure I disagree, but also aren't there other experiments that try and, I think one of the Nobel Prize experiments was involving using
Quantum random
stars
number
to
generators.
set random settings, whatever, using quantum fluctuations. Is that not the same circular argument?
Well, in a sense,
You're still
it is.
requiring quantum mechanics to set the settings somehow.
I mean, in a sense, it is because, well, you cannot really close the freedom of choice loophole. I mean, you can never do it. You can never prove that you have free will. I mean, come on.
But we can do at least as well as the Nobel Prize then with the same argument.
Yes, exactly. So, well, okay. This experiment with the stars, well, it had the advantage of saying that, well, you don't need to assume that the settings are random, but if they were correlated, it must have happened well in the past, okay? In principle, you could find some objects that are so much space-like separated. Because, okay, just to explain the idea of this experiment, the idea was that you register photons from quasars, from very distant objects. And, well, if your photon is, let's say, above some frequency, you make this setting. If it's below the frequency, you make another setting. So you let the stars choose your settings, okay? And then the idea is that, well, maybe the stars have decided to fake your argument, but if they did, they would have to agree, and they must have agreed long time ago. Theoretically, you can find objects which don't have a common past, so it must have been all pre-prepared at the Big Bang, okay? But again, I think it's, well, the idea is to make it more plausible, right? That was this idea of these experiments. In high energy physics, I think the main problem is that it's the same system. It happens in the same system, right? Because, well, you have the stars, which is, well, okay, it's far away, or you can let human choose, or you can toss a coin or do whatever. But that's an external thing. So this is something that you would need to make a plausible Bell test, I would say.
More questions? This one.
Maybe pulling on this thread a little bit more, but what if we prepared our protons in such a way that they were space-like separated? You have two different points, right, that you're injecting your proton bunches from. I mean, yeah, I don't have control over my initial state, but maybe then, you know, I'm letting nature do this selection, but then there's a limitation on how much I could have talked from. I mean, is this a similar idea or no?
No, not really, because in the Bell test that were discussed today, the measurement takes place when the W's or the T's decay. Okay, so it's only then, and then they decay randomly, or they choose their own settings in a way.
Yeah.
So you would need to act directly there.
Yeah. Okay.
So let's thank Michael again.
Okay, thank you.